This will be Mark, Slivero, and Sour Pickles.
Thank you, Matthew. So I'd like to thank you for coming through here to this talk. There's a few options going on at the moment. There's a few rock stars busy speaking, so I do want to thank you for your time. What I'm going to talk to you about today is a module that sits within Python, that's default within Python, that's been there a long time, and that exposes Python programs to a set of vulnerabilities. What this talk is about primarily is on how to exploit those vulnerabilities should you encounter them. So the vulnerability is a known one, but the exploitation techniques here, I believe, are new. Out of interest, who here is a Python programmer? Just raise it. Okay, cool. So I will give you my default disclaimer and say that I'm not a programmer. I happen to be a security guy who plays with this stuff, but I think it's kind of cool. So this is a map of where we're going to be going in terms of the talk today. There's a lot of content to get through. I hope to flood you with information. And if it gets too much, there is a white paper that's on the CD. And these slides are also available for you to go through them at a later time. So we're going to talk a little bit about Pickle, obviously about the background, why we care about it, or why I cared about it, and why it became an interesting target for attack. And then we'll look at specifically attack scenarios. In which instances would you expect to find these exploits that I'm going to show you today? Where would those become useful? Along the way, I'm going to introduce a library of shellcode to you, and I'm also going to demonstrate 3 of those shellcodes that perform various actions. And we'll also release 2 tools today, a tool that can convert basically a Python-like syntax into Pickle. So if you're looking to write shellcode in Pickle, you don't need to handcraft it any longer. As well as a tool which will analyze pickles and help you create malicious pickles. And finally, I'll end off with a few bugs to show that this isn't just all about stuff that we dreamed up, that we did manage to find some of these instances out there. So I want to start off with this big disclaimer. If you go onto the Pickle website, or if you go onto the Pickle documentation, you will see this big fat warning that says, do not unpickle untrusted pickles. In other words, it is known that dealing with pickles that you don't trust is a dangerous action. Okay? So this is on the documentation. However, on the same Python website, if you have a look at the login cookbook, it appears that that statement didn't carry over into all portions of the Pickle tutorial writers. So if you want to, for example, write a login server under Pickle, so if you have an application that writes logs out to a central login server, then the tutorial that you'll come across on python.org is vulnerable to a Pickle loading issue. So this is it receiving data from the network and getting passed into the unpickler. So in other words, the vulnerabilities are present even in example code on python.org. Now on this page, they do have this little disclaimer. Now you notice it's nowhere near as big. They do say in some circumstances, there are some issues, security issues with Pickle. That's nowhere near complete enough. If you expose Pickle to untrusted code, there's always security issues. And by way of example, if you go and Google for this login, for basically that recipe that's in that cookbook, you will find it in production code. You'll find it in projects on the net. So that's pretty typical of what you'd expect. People go online, they look for a quick cookbook recipe, a quick tutorial, they cut and paste code, and they move on. And now their application is vulnerable because the official documentation has a bug in it. Here's another example just to give you an idea of where we can go with Pickle. So this was pointed out to me by a Twitter user, a guy called Dave, DBPH. So what he found in January of this year was that there was a bug in the RSA module for Python. So if you easy installed RSA, and if you use Python, you'll be familiar with easy install, then that RSA module had a Pickle loading vulnerability. Basically, encrypted strings were written out as serialized objects. They were written out as pickles, which was fine. But then he started to look for instances where this module was used, and he came across a little RSA Twitter application where essentially you could publish or read encrypted tweets. And those tweets would be published as obviously Pickle modules. In other words, he found an instance where you had remote code execution via tweets, which was kind of cute. So that's just to give you an idea of where this module gets used, and this is just to set it up, but we are going to dive quite deeply into it. So as we go through this presentation, there are a few goals. The first one, as I said, the assumption is that you get to control what other people load. All right, that's the starting point. You found a vulnerability in an application that allows you to call load S. And when we get into the examples, I'll show you that they're not that hard to find. If we assume that we can call load S with the input of our own making, then the question becomes, well, what can be done? And there's basically one known example. So there's one common example that you'll find in lots of documentation. What I hope to do is convince you of why it's insufficient for weaponized exploitation. It's good, though, for a proof of concept. So we'll look to build shellcode, and then I'll introduce to you a few tools that will help you create shellcode in a much faster manner than one used to do. And then lastly, we'll talk about finding bugs. Right, so ultimately, it's not a new issue, but there's no exploitation guide for this, and the tools don't exist to help you write shellcode for Pickle. So I've got one slide on the background of serialization. There seem to be lots of developers, so I think I judged that right. I don't need to talk too much about serialization. Essentially, you have two processes that want to communicate, and they want to communicate not just with data, but they want to communicate with more rich objects or more rich data structures. And so what they happen to do is they use serialization to convert living objects or living data structures into a byte stream that gets sent somehow, it gets transmitted, and the receiving party can recreate the original object out of that byte stream. Okay. So the background to serialization is pretty basic. I'm not going to touch on it. The one thing I will mention is that those processes don't necessarily have to be separate. So for example, a process can communicate with itself via a serialized stream. In other words, if it writes to disk or if it writes into a database, it's communicating with itself just across different periods of time. So when it comes to using serialization, you've got a few options. You can either try and roll your own, which is probably quite dangerous. You can look for third-party libraries, but generally we'd tend to rely on what our framework provides us until we reach the limits of what the framework provides, and then go looking for alternatives. And Pickle has this, Python has this built-in functionality with this module called Pickle. So when people tend to use serialization in Python, they rely on the Pickle module. Some of the places that you'll find serialized data being passed around, as I say, it's about communication between 2 points, sender and a receiver. So there's a serializer and a deserializer, and that information gets passed through a number of different steps. So it could be on disk, so it could be through a database or a file system. It could be across the network through a socket. It could be into another kind of data store, such as a cache, or even onto a message bus, message buses. But if you're going to do this in Python, you're going to rely on Pickle. I'm primarily interested in Pickle after Python version 2.3. They introduced a number of changes in 2.3 that made this exploitation easier. Essentially, they removed all checks from the Pickle module and said, this is completely non-safe, don't do it. So this bug has been known for quite a while. The reason people would often settle on Pickle is because it is, as I said, a default part of the language. And so if you want to serialize objects, that ability is already there. You don't have to go looking for other third-party modules. In terms of the Pickle language itself, or the protocol, it's gone through a number of versions. So currently there are 6 versions of Pickle, if you go up to Python 3. But actually we're only interested in version 0, and the reason for that is Pickle is backwards compatible. So anything that we write in version 0 of Pickle will be supported by all Python versions going forward. But if we happen to write our shellcode in new versions of Pickle, then older versions of Python wouldn't support it. And the whole serialization, deserialization interface takes place through 2 calls. We've got a call which will create a serialized object, and a call that will take a serialized object or a serialized stream and create the original object for it. So the call which will create a stream of serialized bytes is called dump S, and the inverse is load S. And that's the only two methods that we really care about. If you've used Pickle, you'll also know that there are alternatives to those, so you can also work with files instead of with strings. But eventually it winds up in the same code path, so I'm going to talk in this presentation about load S primarily. And then you also have the options of choosing between a module that implements this protocol in pure Python, but for speed purposes and because Pickles used to deal, or when you do use it, it will be called frequently. There's also a compiled module called cpickle. So as a programmer, you get to pick either use Pickle or cpickle, but their functionality is identical. They both implement the protocol, so everything that you see here is possible both in the Pickle module and in the cpickle module. For consistency, though, I'll stick with just the Pickle module. So some terminology, if I talk about Pickle with a capital P, I mean the module. If I talk about Pickle with a lowercase p, I'll talk about the sequence of serialized bytes. I'll rely on you to tell the difference if I'm using a capital P or a lowercase p. I kid. I will also talk about a Pickle stream as opposed to simply talking about a lowercase pickle, which may give you more of a hint when I'm talking about a serialized stream of bytes as opposed to the module itself. But apart from that, we've got two other terms that are of interest and will be somewhat new to you because I used them in my paper. The first is a host pickle. This is a pickle that you come across somehow, and it's one that you are able to control completely. So this is the thing that you get to write into. That is the host pickle. A mel pickle or a malicious pickle is one that you've you've written shellcode into. All right, so we've got a host pickle, and when we write bad stuff into it, it becomes a mel pickle. And then if I talk about pickling and unpickling, that's just verbs for serialization, deserialization. That's Python terminology. Then the last part of the last terminology that I'll introduce is the idea of an entity. In a serialized sequence of bytes, what you'll find is embedded in there are strings, integers, other types, and so on. But each of those things is has a type. It's an object that exists within that serialized stream of bytes. And so that is an entity. We may have a string entity, we may have an integer entity, we may have an entity that is a more complex class than just those basic types. But we have these blocks inside of a pickled object that I term entities. So if we start to peel back the layers a bit, one of the reasons why one uses Pickle or relies on Pickle is because it's not just about carrying data structures. At the end of the day, you get usable objects, living objects. And Python is quite smart in this way because it is able to handle arbitrary objects. You can serialize any object, well, not any object. If you're a developer, you'll know that statement's not true. But you can serialize objects that the pickling module knows nothing about. So it is possible for Pickle to create serialized objects without knowing anything about the object that it is trying to serialize. The only requirement that the Pickle module has is that it can reconstruct an instance of that object that it is trying to create. In other words, is that object, does it have a constructor available in the current environment? And so as I mentioned, this call to load_s, that's the gateway to our exploitation. So if you're looking for an analogy, load_s is somewhat like get_s in the world of memory corruption. We may have a get_s function which will blow past various items in memory in say a C program. But the way that you exploit it varies completely. So depending on the nature of the environment, get_s, the way you'd exploit get_s could change. And it's the same with load_s. So load_s is our vulnerable function in Pickle. What I aim to do here is explore the various ways that one can blow past Python and get shellcode running. So to look at a very high level on the pickling process and the unpickling process, this is essentially what happens. Now it glosses over very many details, and so it's not designed to give you a full insight. But essentially, when you're trying to create a serialized object from a stream of bytes, the Pickle module will extract the name of the class instance that it is trying to write out to a stream of bytes, and it will also extract a list of the attributes that are unique to this instance of the class. In other words, we can frame it even more broadly and say it pulls out a list of all the local variables. It's not entirely true, but it works for the purposes of this. So we have a list of local variables, and we have the name of the object, and those get written out into a structured way into the stream of bytes. And on the other side, when we try to create the original object, the unpickler will first read out the name of the object that it's trying to reconstruct. It will read out what are essentially all its local variables, and it will create an instance of the name of the class that was stored in the Pickle file, and then it will apply all those local variables to this newly created object. So now you've got this object that's living, it's got the same parameters as the side in which created the serialized object. So Pickle has this, as I say here, really expressive language because it is specifically focused on producing various data structures. So it is very strong at carrying data. So if we get or look a little closer, or even further, if we look even closer, sounds better. What we'll do is, as I mentioned, load S is the entry point, but actually underneath load S lives this virtual machine. So Pickle does not just rely on data structures. It's not just about length, type, length, and value, or length, type, and value. Pickle actually relies on a virtual machine to produce the final object. And so what that means is that a pickled object is not just data, it's actually a series of instructions and data that are interleaved. And the instructions, these opcodes, are going to be provided to a virtual machine which will process this instruction sequence. And at the end of it, what comes out is an object. Okay. So the PVM has got it's basically got three components to it. There's the part that manages to process the instructions, the opcodes, that's the engine, and it also has a stack and a memo. So the instruction engine starts reading from byte 0, as you would expect. Depending on the Pickle version, in truth, it may also perform content snooping to determine a Pickle version. But that aside, it will start at byte 0 and read the first instruction. That instruction will instruct the engine to do something with data that is stored inside the stream. It may load that data onto the stack. It may change the stack. It may alter the memo. But the point is that we've got instructions and we've got data that are mixed together. So if the instruction engine drops into the middle of a Pickle stream, it can't tell if it's in the middle of data or instructions, which may sound somewhat familiar to you for memory corruption. So as it goes through the instruction sequence, it will execute each instruction in turn, and it will alter its memory structures depending on what it gets told to do. And it keeps doing that until it encounters a final instruction called stop. And what stop does is it takes whatever object is on the top of the stack at that point in time, and it returns that thing as the result of the unpickled process. So that's actually how an object gets produced. You manipulate data through this PVM. That object, and at the end of this manipulation, an object should be living on the stack, and that object gets returned. So the second part of the PVM is the memo, and the memo is analogous to registers on a regular machine. So you get to write into this data storage, and what the benefits of the memo are that it is long-lived. So you can write data into the memo, and that data persists throughout the lifetime of the Pickle virtual machine. And what is also nice about the memo is it's implemented as a sparse array. So you don't have to write and read from, or you don't have to write into all values from 0 through 9 before you can write into value 10. You can immediately access entry 10 in the memo. And that becomes interesting for us for writing shellcode, because we're going to rely on the memo, but we can choose or a set of the memo with high index values so we don't tramp over parts of the host Pickle. So what I've got here are two instructions. The first instruction is an S instruction. This loads a string, and it loads that string from the instruction sequence, and it places it onto the stack. It pushes that string onto the stack. Then the second instruction takes whatever's on the top of the stack, and it loads it into the memo. So you get an idea of the instructions. Because we're dealing with version 0, the Pickle is entirely 7-bit, so we can read it in just a text editor. Then the final part of the PVM is the stack, and that is a normal stack. It provides local storage for blocks as they work through, or basically it provides local storage in the PVM. And when it comes to the stack, what you'll find is that the instruction sequence primarily deals with, or the opcodes primarily deal with the stack. So opcodes only load data onto the stack. They can't load it directly into the memo. So the sequence is normally load data from the instruction sequence onto the stack, and from there process it and maybe shift it into the memo if it has what you want it to have. And as mentioned, at the end of this whole execution, whatever's on the stack becomes the deserialized object, or the top thing on the stack. So that leads us to Python instructions. And in terms of the Python instructions, the PVM instructions, what I want to say here is that the opcodes are not equivalent to Python statements. So Pickle and Python are not the same thing with separate labels for their methods or their statements. Pickle has a very clear and distinct instruction set, and that instruction set is focused on processing data. It's got nothing to do with Python, except that there are Python implementations for Pickle. And that Pickle has built-in opcodes for dealing with Python data types, but that's where the overlap ends. So the opcodes are single byte. There's quite a few of them, and basically that's where the protocol version gets determined. So through subsequent versions of the Pickle protocol, more instructions are added, but it's also why it's backwards compatible. They don't change the meaning of old instructions. Instructions are just added to the set. And as mentioned, what we can do with the instructions is load data, which is mostly what happens, but we can also create objects where it gets interesting, and we can manipulate both the stack and the memo. Then the last point there is something that I'll touch on again, and what it says is that there are no instructions that enable the instruction sequence to modify itself. So if you're trying to introduce, for example, looping or repetition by modifying the instruction sequence from within the instruction sequence, we don't have opcodes for that. I do have a proof of concept that kind of allows that, but we won't talk about that today. It's pretty hacky. Okay, so in the white paper and in the original set of slides, I had a whole bunch of text on the opcodes themselves. I've removed that to save some time. If you're interested, go read those. But on the left-hand side, what we've got is an instruction sequence, and on the right-hand side, we've got a stack. And I'm basically going to quickly step you through two examples of how the instruction sequence gets processed and what happens to the stack. So as you can see, that instruction sequence is readable. The new lines there are intentional, so the new lines would be embedded inside of the instruction sequence. The first instruction that we have is the round bracket. It's called a mark object, and this is used as a placeholder on the Pickle stack. And I'll show you now why that's important. But firstly, we push a mark object onto the stack. We then push a string object onto the stack. We push a second string object onto the stack. We then push an integer object onto the stack. So the stack layout now contains two strings and an integer. Then the final instruction that I've got there is T, and what T does is T goes onto the stack and it pops everything off the stack until it hits the first mark object. It then packages together all of the items that have been popped off the stack into a tuple. So our next, or after the T instruction has been executed, we now have a tuple living on the stack. And so this kind of data manipulation is what Pickle is really good at. We can load individual kinds of attributes, and then we can package them up into tuples or lists or dicts or whatever the case is. The next example, though, is where we start to encounter why Pickle loading is dangerous. So in this example, what we're going to do is to call a method. But we have to break it up into two parts. The first part is to load onto the stack a callable object. So if you're a Python programmer, you'll be familiar with the idea of a callable. So callable, if you're not a Python programmer, we're used to functions and methods being callable. In other words, you can execute them. But in Python, you're not limited to just functions and methods. Classes can also be callable, for example. So the idea of a callable is anything that can be executed as if it were a method. And what the C instruction does is it loads in two parts, a module and an object out of that module, in the top level of that module. So what we're doing here is we're loading a reference to the built-in file class. And that happens to be callable. In this case, it's not a class, it's actually a function in the top level of the module. But from Pickle's perspective, it can't really tell the difference. So it can load any top-level object from a module, even if it's not callable, it turns out. But we need it to be callable in this instance. So that was our first instruction. The second instruction loads a mark onto the stack. Third instruction loads a string onto the stack. And you'll see the fourth instruction is a T. If you remember what T does, pop everything off to the mark, load a tuple. So now we have a tuple sitting on the stack. Below that is a callable. And below that is the rest of the stack. Now the final instruction that we have is reduce. It's R. And what R does is it takes that callable and it applies that callable to the tuple that was also sitting on the stack. In other words, we get to call a function with data that sits on top of the stack. And whatever comes back from that function execution or that function invocation gets pushed back onto the stack. So now what we have on the stack is no longer the callable or the tuple. What we have on the stack is an open file object. All right. But this is how Pickle is supposed to work. There's no, at this point, we haven't shown you anything new. Pickle should do this. And we shouldn't be surprised that Pickle can do this. But there are a few limitations to what you can do just sticking with basic exploitation like that. So, for example, with Pickle, you can't pickle objects that are context dependent. So consider a network socket. To pickle that doesn't really mean much, or to pickle an open file. In order to recreate that situation on the other side, you'd also need to transmit the file or the entire status of that network stack and so on. So not any object can be pickled. In terms of the operations that are possible on a pickled, or the opcodes that Pickle supports, so that set isn't Turing complete. So for example, there's no comparison, there's no branching instruction. So you can't write fully fledged programs just in Pickle instructions. You also don't have any error handling in Pickle. So you can't, if your Pickle breaks, that's it. It dies, and unless you're catching those exceptions in the outer Python program, you'll see broken programs. But probably the primary limitation that we see is that it's not possible using Pickle opcodes to execute instance methods. So a class instance is obviously an object that's been instantiated when a constructor has run. And it's not possible using opcodes to call methods on instances. So our primary goal then is going to be trying to bypass that. And what we'll do is rely on a combination of the instructions that we have, which is the ability to load objects onto the stack and the ability to call callables. And we'll use those to try and bypass this class instance method invocation limitation. There's lots of words in there. I hope you can follow along. If you're a Python programmer, it's probably making sense. If not, wait for the demos, I suppose. Okay. So if we look at previous work, basically that's where the previous work stops. There's no focus on trying to return information out of the pickle, which is what we'll deal with. And there's also no ability to execute class instance methods. Okay, so I've talked for quite a bit. I want to do a quick demo just on how, if you're unfamiliar with Pickle, let's do a quick demo on exactly what happens. Okay, so I can instantiate an object. This object has got a number of attributes. And what I can do is so what I can do now is I can pickle this object. Right, I can write it out into serialized form. So that's what that object that I instantiated looks like when it's written out into a serialized form, and I can load that serialized object like so, and what I get out of that is a talk instance. So that's just showing you dump s and load s, and they're the inverse of one another. And so we can call so what we can do is call methods on this object. So I've got a method here that's called won't make changes, which if we pass data into it and have a look at our pickled object, that's still exactly the same as the object that we received back the first time. In other words, not everything gets pickled, even though I'm passing information into the object there. It doesn't get stored in the pickled object. This method will make changes, and so that's because it stores essentially a local variable, which is why I want to use that very rough abstraction. So what you see here is the string that I wrote in now gets stored in the pickled object. Okay, but don't get too caught up on that. It's basically the idea that we can load and dump serialized objects, and only some changes that we make to a pickled object or to a Python object show up on the pickle side. So with the idea that we can call load-s on or inside of programs, the question then becomes, well, what kind of attack scenarios would one typically see? So you may be familiar with loading off the network, as I said, with the logging issue, or it turns out you can also do it via a Twitter module because someone has coded it. Because serialization is used to communicate between processes, it really is up to you to think of how that could happen. This is one tree, one attack tree, which we've seen. And you'll find that it's quite network heavy, so communications between clients and servers, where one of those parties is untrusted, or even a man in the middle if you're not relying on some kind of transport layer protection. But also, in terms of file handling, we found Pickle vulnerabilities. So programs that write to and from the file system in an insecure way could open you up to Pickle handling issues. And then last year, and this is actually the part that kicked this, or this was the process that kicked off this talk. Last year, we found an instance of Pickle loading vulnerabilities where Pickles were being stored in caching servers. So we've got examples of all of these instances of Pickle loading vulnerabilities. But to make it a little more concrete, here are some examples. So you have an application that persists data out to disk, and as I said, that application may use insecure file permissions that allow other users to overwrite the file. If you take, and again this was pointed out to me by Dave, if you take a tool like Scapy allows you to save sessions to disk. And if you pass a Scapy session to a colleague or to a friend, that is stored as a pickle. So if you work with people and you are reliant on passing saved Scapy sessions around, you better trust those guys who you're getting your Scapy sessions from. So it doesn't just have to be about file permissions, it's also about storage of data. So if you think of storing data in a pickle format, it's analogous to storing data as a DLL or a shared object, a shared library. That's essentially what you're doing if you're storing data as a pickle. You're storing it as a library that can be executed. Another example of vulnerable applications would be Python modules that store their cookie information in a pickle and send that pickle to clients of the website to pass back as part of the cookie, which was a vulnerability that existed for a while in quite a popular web framework. It has been fixed though, well, quite a while ago it was fixed. And then lastly, we have thick applications, and we'll look at some examples a little bit later where communications between components in the thick applications use some RPC mechanism, and over that they pass pickles. So if we assume again that we can control the input to load S, wherever it sits, it's either on the network or it's on the disk, somehow we can control what gets passed into load S. The question then becomes, well, if we want to change the pickle, how can we go about changing it? Our options are, we've got a few. For example, we can completely overwrite that pickle with the shellcode that we put in, right? So there's no part of the original host pickle is left, it's just mel pickle. Or we may put our shellcode at the end of the host pickle, or we may put our shellcode at the beginning, or we may insert our shellcode in the middle somewhere. So the question is, how do you choose? And so I'm going to do this with diagrams and show you the benefits of each of these approaches and the drawbacks. This is a normal situation. We've got a pickle stream at the top. And this pickle stream gets loaded into a Python program through this load_s method. And when the pickle stream, or when the load_s method calls, the PVM runs over this instruction sequence, and as output it produces an object that gets assigned to O. And what happens is, that object now is a live Python object. In this case, it's of type foo. You'll notice that I've got data in the pickle stream. I've got entities, strings, which are yellow here, and integers, which are green. And that data, when the PVM finishes executing, gets placed into this live object. So you can see then that that data becomes accessible inside of the object. And then later on in the Python program, the original Python program, it's possible to call methods that this class supports. For example, o.yes. And then the application can continue executing because it's dealing with an object that it expected. However, if you truncate, if you completely overwrite the pickle stream with malicious shellcode, then it changes a little bit. The load_s call still works completely. That works 100%, no problems. That's because the shellcode is well structured. But what's different is the object that is left on the stack once load_s finishes executing is not necessarily of type foo. It may be of some other type that the attacker happens to leave there. And let's say that that object is of type shellcode. And so later on in the original Python program, when it tries to call o.yes, unless the shellcode class has a yes method, then you will get an exception. You'll get no attribute find error, and an exception gets thrown, and now the program dies. So even though your shellcode executed, the execution of the outer Python program died at a later point. Now that may not matter to you. Your shellcode may be completely self-contained. It may do whatever you want it to do. Maybe it's to write something to the file. Maybe it's to open up a listening network socket. So maybe this situation is all right. But if you're looking to extract information out of the pickle, then this is not the way to do it. And the same happens when you append shellcode to the pickle stream. You get the same situation. Even though the original host pickle will execute and it will leave its object at its top position on the stack, the shellcode then runs after that. And so the shellcode will leave its object above that of the original pickle stream. And at the end of the loaders call, what gets loaded is now an object of shellcode, of type shellcode, and will die later with another error. So here are the two that we would prefer. If we put that shellcode at the start of the pickle stream, then it can execute, do whatever it wants, leave the stack clean, and then the original shellcode will be loaded. Sorry, the original pickle stream will run, and the output of this is an object of type foo. Okay, so we can execute shellcode and have the program not break, which sounds good. But an even better option is if we start to inject in the middle. So if we start to replace parts of the entities inside of the original pickle stream, what we can do now is have our shellcode run, and when it executes, it produces output. And that output then becomes one of those entities inside of that object. And so when the object gets loaded, when the loaders gets called, we produce an object of type foo, but our output has now replaced one of the entities inside the original host pickle. And so now we have a way to execute pickle streams of our own choosing and have them show up in the host pickle, which becomes quite interesting for extracting data. Okay. So the verdict there is to either prepend if you don't care about output, or if you do care about output, then overwrite an entity and make sure that the types match. If the entity that you're overwriting is an integer, your shellcode can't produce a string. The instructions won't match and it will die. So when it comes to writing shellcode, there's two approaches that you'll find on the net. The one is to handcraft it, as you can see there at the top. And the second one is to generate it. Now both of these have limitations. So the first one doesn't allow us to extract output. It's not strictly true. You can extract output in the exit status of os.system, one character at a time, but that's very, very hacky and also quite slow. So let's ignore that approach. The second one is to use Python to generate objects for you. So here we use Python to create a pickled object for us, but that approach isn't general enough. Interestingly, that was published by, I think, a guy called Nelson Elledge, and he's speaking, or I think he was speaking here at BlackHat the last time I checked. Okay, so some of the principles when it comes to writing code, we want to stick with version 0, as I've mentioned. In fact, most of this we've already touched on, but right at the bottom, that is the base pattern that we're going to rely on, the ability to at least execute a callable with data that we choose. And so we're going to start to piece together various steps that allow us to, in the end, execute methods on class instances. So here are a few guidelines for writing shellcode. But the first, I don't want to go through all of them. The one, though, that I do want to talk about, well, two, we'll make it one. I'll talk about number 6. I'm aiming for reliable and deterministic shellcode. It's possible to write very simple shellcode that hard codes lots of values. So things like what is various network parameters, are they hard coded? And if they are, then that would mean that they're specific to each operating system. So if you want to set socket opt on, or set sock opt on Python, you would normally do a lookup on a module constant. It's possible to encode those in your shellcode as hard constants, but that doesn't make them reliable. So that means your shellcode won't work on macOS if it works on Linux. So I'm looking to create deterministic and very reliable shellcode. And so in order to build a shellcode, we've got a few building blocks we need to get through. The first one is that we have to be able to call methods on class instances, and this is the problem. So what those first two lines show you is that if we open up an object, for us to call f.read a read method on that class instance, there's no way to do that in Pickle using Pickle opcodes. But we can get there, and we can get there because we're able to load other objects and callables, and we can play with data structures. So the two instructions we rely on, again, global and reduce. This is the ideal stack layout that we want. We want a tuple for that f.read, which is an empty tuple. And underneath it, we want a callable that represents that instance method. Getting to this point is easy, right? We can generate tuples without a problem. It's producing this callable on the stack. That's going to be the trick. And so the way we'll do this is through Python introspection. So we have these two statements that we're trying to reproduce in Pickle. As I said, the first one is easy. We can create an open file object just by calling built-in.open. And what that'll do is this sequence of Pickles saves that open file object into the memo. Then the next step is to get to basically call f.read. And I don't want to go through it here. My time, I see, is going to be tight already. But essentially, we rely on Python built-in. We rely on a sequence of apply, get attribute, and a class, reference to the class. And using that, we can simulate calling f.read. Okay, so that last line is the line that is the important one. That's what we've tried to derive. So we go through each of those stages, and finally, we get to this line. And to convert that into a sequence of Pickle instructions can be done. So that's what you've got on the left-hand side, is f.read converted into a sequence of Python introspection hacks that ultimately allow you to call f.read. But this doesn't really suit what we wanted to do, or it doesn't really fit our guidelines, mostly because they're composed. So we're calling f of g of x, essentially, when we layer all of these functions on the stack. So the preferred way to do this, if you remember, or what I mentioned in the guidelines, was to deal with a very clean stack. So this is a more general template for calling an instance method for some arbitrary class. And so it calls, if that is the class that we want to call, sum.class, that's the method name that we want to call. And you basically can take this template and put in the values that you need and get that to call instance methods for you. So in all, this is then our shellcode for opening, reading from a file, and closing the file. That opens the file. You can see it's a tiny bit of shellcode. This next one is to get a handle to the file.read class method. And if you're a Python programmer, you'll know the difference between a class method and a class instance method. But this allows us to get a reference to the class method. We then apply the class method to the data that was stored on the stack, in this case, the file handle. And then lastly, we call file.close. And as the result of this whole shellcode, we return the data that was read. Then the second template we'll look at is accessing module constants, and this just helps you develop consistent and reliable shellcode. Here we load a reference to the module's dict object, in other words, what its attributes are. Here we load a reference to its getItem method on that dict object, and finally we call that method with the constant name that we want, and we can now return module constants. Okay, so we're almost at the demos, but there are a few considerations. So the first is when you write the shellcode, how are you going to do it? Are you going to write everything in Pickle itself and try and map that to a series of Python calls? So for example, if you want to open file, read a file, and close it, you can do that all in Pickle because there's Python methods that are available to you to do that. But there's another way to approach it and to say, well, let's try and parameterize our exploits. If we can write one Python or one Pickle shellcode that accepts as input something else, another language that's easier to write code in, then we can build much more complex exploits. And so what you'll find is that you can, for example, parameterize the shell. In other words, open up bash, and now you pass into this, or what you embed in the Pickle is actually bash. That will do the things for you. But the one that I'm more interested in is when you embed Python inside of a Pickle, which gets executed inside of Python. So it's somewhat like Inception. We just keep going through many, many more layers. And so there's also discussion that takes place in the white paper on back channels. I'm going to ignore it here, except to say that the examples that you see mostly will show up the output as part of, for example, a web page, but that doesn't have to be the case because you can call any Python method. You can also call your own output functions. And there's one demonstration with that. There's no real limitation on length when it comes to shellcode. Not that I could see. You're basically limited to Python strings, which are pretty big. And the last one is about creating, or the second last one talks about creating persistent shellcode. In other words, can you have shellcode that runs throughout the lifetime of that Python execution? So not just the PVM, the virtual machine, but actually in the Python object, or sorry, the Python thread that called PVM. And I'll show you that that is also possible. And so with these templates that I've given you, it should be clear that there's nothing particularly special about them. They're just templates. And so we can map from Python calls into Pickle templates. So it's possible to automate this. And so the first tool is this thing called convert-to-pickle.py. And it takes as input a series of Python-like statements. It's not Python, but you can see it's kind of Python-like. And they're annotated. So at certain points we say to convert.pickle, the object you're dealing with now is, for example, a file type. So it doesn't have to try and figure that out. And what it can produce is a reliable Pickle shellcode. So now you get to write your code in this higher level Python-like language and run it through convert-to-pickle, and what comes out is Pickle shellcode that'll do what you want. So that's kind of useful because at this point you don't need to care about opcodes anymore. So you don't need to know anything about opcodes. You can write in Python-style code and you can get Pickle shellcode out of that. So we wrote a whole pile of those, and we got this shellcode library. And you can read through there very quickly the things that's possible to do inside of a Mel Pickle. But I'm going to focus on 5 of them. I'm going to focus on showing you a reverse shell. I'm going to show you running eval on supplied Python code. I'm going to talk about injecting a Python debugger using settrace, and that's how we get the long-lived execution. And then also look at 2 frameworks, so specifically Django and App Engine, and what may be possible to do in Django and App Engine. So with the first one, with the reverse shell, what we've got here is this is the input to convert to Pickle. So this is a series of Python-like statements that open up an outgoing network socket, and once the socket's connected, it binds a shell to it, which is what there's nothing particularly special about it. When you run that through convert to Pickle, your shellcode looks something like that. And so while it is possible to hand craft that, it's going to take you some time. So the benefits of having a conversion tool should be quite clear. Okay, so let's look at a quick demo here. So the site that I'm going to demonstrate this on is a Django site. It's just a test site that we've got. And it's very clear. It says it nakedly loads Pickle strings, all right? So don't focus on the fact that I'm pasting a Pickle in. This may be carried over in a cookie value. This may be as part of an RPC mechanism, whatever the case is. But basically, we've got a service running somewhere that allows us to paste in or to provide it with Pickles. And this particular Pickle I've got is the reverse shell code. Okay, so I'm going to start up my So I'm starting up a listener here. I go onto this other website. It's sitting somewhere in the net. We hit load, or we basically submit the Pickle, and what pops out is our reverse shell. So now we're getting the Python interpreter that executed that Pickle. It runs through that Pickle instruction sequence, and as part of that Pickle instruction sequence are a whole bunch of calls to global, reduce, and so on, that eventually wind up calling an outgoing network socket and bind a shell to it. So we've got a full shell there. So that's the first demo, just showing that a reverse shell is possible. The next one is talking about eval. So eval is a Python function that will take as input Python code and execute the Python code. And so we're not far now from the reverse shell, except we're no longer just producing a network socket. We're running parameterized code. And this is, as I say, where it gets quite fun. So for example, our parameterized code may be the following. The parameterized code may be something that calls out to a website, grabs all the content of the website, and loops through the content and then inserts the output of that website into the pickle that the page or the program is dealing with. Now, why I like this example is because this is the way you can get error handling, repetition, and branching inside of Pickle. You parameterize a Python program, and the Python program is able to loop and do whatever Python can do. So the next example on eval is, just to be clear, so I'm not leaving anyone behind here, we're going to paste in some shellcode that has, as part of it, a Python eval call, and as part of that Python eval call is an embedded Python program. So we're calling eval in Pickle on an embedded Python program. And that will be, so if we look inside here, you'll see that you've got, and it's all escaped, but there's our try, there's our for L in URL lib2.url open. So there's an embedded Python program that lives within this Pickle. And so when I hit load it, what I would expect to do if my internet connection is working is that this Pickle gets submitted to the listening web server. The listening web server tries to depickle or unpickle this object. And as part of the unpickling process, it will go and fetch data from Google. And that gets inserted into the Pickle that was, or the final object that gets recorded. So the final object that comes out of that unpickle process has within it an embedded web page, which is Google. And then as part of my demonstration, I just output that object. So in other words, I'm showing you that it's possible to do things and return the output within the current channel, which is a web page. Okay, so down here, what we've got then is, as part of the output of this object, we've got the Google web page over there. Okay, so we can use Pickle to return values, or we can even construct our shellcode such that the value is returned as part of the Pickle itself. We're doing a replacement of entities. Okay, so that's eval, and we've just done that demo. Then the next demo that I want to talk about is setTrace. And so setTrace is a debug function within Python. It allows you to specify a method that gets called on every line that gets run or in every method that gets executed. In other words, it's for implementing debuggers. Now what we can do is we can combine our eval shellcode with a piece of Python that creates this debug hook. Okay, and this is where it gets kind of sexy. So our program, this is one trivial example of what is possible. So we can inject a function that gets called every time there is a call event. In other words, every time a method is entered. And all our code does here is it prints out the local variables for that function. But that's quite a toy example. We can make this a little more interesting. So consider the exact same function there, except instead of printing out local items, what I'm going to do is I'm going to make a web request. I'm going to make an HTTP request to a listening HTTP server somewhere else on the internet. And so now we can remotely debug someone else's Python server because they're vulnerable to a Pickle loading issue. So I've got a few things running here. What we have here, nope, not there. Okay, so this little program is just an HTTP server that's listening for incoming connections to it, right? That's all it does. It sits somewhere on the internet. We find a Pickle loading vulnerability in a website, and we've got this piece of Pickle shellcode which calls eval. And on eval, it will set the setTrace method. So now what we've seen, so the Pickle loads without breaking. And if we switch back here, what you'll start to see is those numbers are changing, right? In other words, every module or every method that gets called in the Python thread that lives somewhere on a web server on the internet is generating a call event. And every time there's a call event, our debug handler gets hit, and our debug handler is posting that information elsewhere on the net. So if I refresh this page, you'll see all the methods that get called return their values to us. So we start to see things like, we're going to have to scroll up here, but you see the local variables that are relevant to that particular invocation. So you'll see things like the CSRF tokens and all of that. Right? You have direct insight into the running of that Python application, which becomes very powerful. And of course, we can also disable it remotely. So once we've got everything that we need, we can just disable our remote debugger. Then if we look towards the frameworks, we can start to get framework specific. So sometimes you're not just interested in executing code, or you're not just interested in debug hooks, but you want to just find out a little bit more about this particular framework. And so if we take Django as an example, you can send email via Django if you wanted to, create your pickle to send email. But more interesting is you can start to do things like query the configuration settings for Django. So if you know anything about Django, you'll know that there's a secret key, and that secret key is used to generate CSRF tokens and so on. It's used as the basis for some of the internal crypto. And so what we can do is, if we've got a pickle loading vulnerability in a Django application, we can ask, as part of our vulnerability, or as part of our malicious pickle, we can say, please return the value. So look up in your configuration and return the value of the secret key. So there's the secret key from this Python configuration, from this Django configuration. So now we're in the position to spoof requests to the Django server on behalf of other users. But it doesn't just have to be about this. You can also query the databases and so on. So let's have a look at one example of that. My example is not going to be in Django, though. The example is going to be in Google App Engine. So in Google App Engine, it's also another Python web development framework. And so again, if you find a pickle loading vulnerability in an App Engine application, let me stress that I'm not revealing vulnerabilities here in either Django or App Engine. I've coded specifically vulnerable applications. But if you come across those, and Django has had issues, then these attacks are possible. And so what we do in this particular input to App Engine, this little program here is what we pass into convert to pickle, and it'll produce the right shellcode. And as part of this, it's actually an eval shellcode. And what we pass into the eval shellcode is a query to the Google store. So the layers that we're currently dealing with, at the bottom, you've got Python. It's running as an executable. On top of that sits Pickle. On top of that, we're evaling Python code. On top of that, that Python is then calling the Google query interface. Okay, so we really have dropped down a number of layers. I should have put that in a diagram, I think, just to shout. Yeah, thanks, Dominic, who told me not to do that. So what we can do is query the data store and pull out all the types of data items. So the first step is to find out what kind of things are stored in the database, and we can do that with this query against an App Engine application. So our shellcode to extract all the kinds of properties. Again, the application is very rough and ready, but that's not the point. The point is to demonstrate the shellcode. What I see here is that we've got this kind of property called greeting with a name. It's got a property author, it's got a property content, it's got a property date. If you've played with App Engine, this is the 101 application for generating App Engine apps. The vulnerability, though, was introduced by myself to play with this stuff. So we can pull out all the kinds of Python objects that are stored inside that data store. And once we know what kind of objects they are, we've got this greeting, and greeting has got author and content. We can then write a second piece of shellcode that includes a query against that object, right? We now know we need to query greeting and pull out all the authors and all the content. And so now we can query the Google data store with a query that pulls out the contents of the data store. So using Pickle, we can now query, as I say, the Google data store and extract it completely. So we can first recover its schema, and then from that recover its data. Okay. So the second tool we'll release then today is a tool called Pickle. This tool is to help you create malicious pickles, essentially. So what it can do is it takes as input a pickle that you've obtained from some source, and you get to analyze it a little bit. You get to extract the entities that are in there, and you get to overwrite entities in a way that is type safe. So Pickle will go to some length to make sure that all the types are the same. If you try to overwrite entities where it doesn't think you should, it will complain about it. So it tries to apply a little bit of intelligence in that process. So we're going to demonstrate this, and my demonstration is going to be on another toy website. So on this, so this is the App Engine website. What you'll find actually, we need to be here. I will give you the layout of what I'm doing shortly, but essentially what we've got here is a web page where you sign stuff into a guest book, and that gets added at the top. And if you have a look at this, if we have a look at the page source, what we find is there's an embedded object in here, which we're not too sure about. But what we see is it's base64 encoded. Okay, so like any good web hacker, you see base64 encoding. First step is, well, what is that about? And when we decode it, what we see, it's a pickle object, random.nonce. Interestingly, if we try to load that object, it will fail because our local Python interpreter doesn't know anything about this random nonce class. But I won't show you it failing because time is running out. So what we see here is a base64 encoded pickle stream. So what Pickle will allow you to do is to start to play with this. So I paste that into a text file, and I can now ask Pickle to analyze that for me. So -n just says it's base64 encoded. I point it at there, and I ask it to run a whole bunch of tests on the file. And so it comes back and it says a few things. The first one is it says it could not be loaded, and that's because the local Python interpreter doesn't know about this random nonce class. But that's okay, we're not too concerned. More interestingly is it gives us a list of all the entities that are present in this class. We've got this, and what we'll find is that there's this entity, a really long string here that appears to be some kind of nonce. But if we go back to our web page, what we saw is that after we submitted the data, we got redirected back to a URL that included this nonce. Okay, so the question then becomes, well, maybe we can extract data using that nonce as our channel. So what we can do is we can start to modify. So if we know that these are the entities, we've got entity 0 is a string called nonce, entity 1 is a string that is this whole long thing. We can overwrite entity 1 with a piece of shellcode that is stored in our shellcode library. And this one will return the application ID. Just to give you an idea of what options are available in the ID or in Pickle, we've got a whole lot of shellcode. The library is basically embedded in there, so feel free to go check that out. But ultimately, what we produce is another base64 encoded string, and this base64 encoded string, if I can show you, contains the original object, random nonce, but part of it seems to be overwritten with Google App Engine stuff that we've inserted into there. Okay, so now the process is, again, we're going to submit something to the guest book. I'm going to just trap this in our proxy. I've got the signal. there's that base64 encoded pickle string. When we continue, what I expect to see, if this is successful, is that the redirect that comes back, instead of redirecting with the nonce in the URL, it should redirect with the output of our pickle in the URL. And so what we'll get here is that string there. May not be completely readable to you, but what we've got there is not a nonce now as part of the value, but it's actually the name of the application, the app ID. So this is just to show you how it's possible to use AnaPickle to manipulate quite easily malicious pickles that one comes across. Okay, so I don't need that anymore. Let's get back into this. Okay, so with this, we then went for a survey to find as many bugs as we could find. So with this in mind, and we looked on a few places: Google Code, Knowledge, SourceForge, Google itself, Pastebin, and so on. And basically, you're searching for bad calls. And bad calls can be obvious things like pickle.loads on packet, but it could also be in a combination with the decode and decompress and so on. But there's a few ways to find it. Alternatively, you can just start reviewing code and the way that they call loads, and you'll also find vulnerabilities that don't pitch up. And so in terms of our survey, it appears that the issue is not endemic. So you don't find this on every second application that you look at, but you do find it. So we didn't have to look particularly hard to find examples of each of those classes of attack scenarios that we were after. So you'll find them in all of these options. So I've got 5 examples to talk about. The first example is basic web kind of code, and basically this loads pickles out of web requests. So it's sort of 101 errors, and those are quite easy to find, and you'll find quite a few examples of those. The second one is this tool called PyTables. So PyTables is a library for wrapping around database or databases, and as part of the PyTables library, it's possible to create tables. And one of the parameters given to the create table method is a title. And that title is vulnerable to a pickle injection flaw. So if you allow users, if you have an application that's written to use PyTables, and that application allows end users to create tables and specify their own table names, then it is vulnerable to a pickle loading bug. Third example, and we'll do a demo for this one. So anyone here use Peach Fuzzer? Okay, so Peach Fuzzer is vulnerable to pickle loading vulnerability. Peach Fuzzer, if you use it in a network setup where you have an agent and a fuzzer that sit on either side of a network, then they communicate using pickles over the network. Now, Peach Fuzzer puts a password on that connection. So when the agent connects to the fuzzer, there should be a password that's exchanged. Or when the fuzzer connects to the agent, there should be a password that is exchanged. But it turns out the vulnerability occurs prior to the password, so it's a pre-authentication issue in the Peach Fuzzer using Pickles. So I'll demonstrate that for you. And the demonstrations are... Okay, so I need to just set up that. Okay, I already have my fuzzer, I already have the agent listening, so we're all good. And so basically I've got the agent listening somewhere on the network, I've discovered it, and I run this exploit, which I'll show you the code for shortly. And now, if I can remember the port number, I connect to that agent on port 12345, and I have a shell with the permissions of the user who is running that Peach agent. Okay, that particular piece of shellcode looks something like that. Okay, so that gets you a remote shell on a Peach fuzzer. So what's interesting is that the author of Peach is aware of it, and they are looking to change it. But if you're running Peach on a network at large and it's not isolated, then you're in trouble. Interestingly, the Sully fuzzer, anyone use Sully? Also vulnerable to the same problem. So if you also run Sully on untrusted networks, you probably want to shut that off. Okay, second last example, a tool called Tribbler. Tribbler is a research project out of the Netherlands and essentially what they're trying to bring is streaming video onto BitTorrent. But as part of this research project, they allow researchers to connect and gather statistics from participants within this peer-to-peer network. And they use, as is obvious at this point, they use Pickles to communicate. Now, it opens up the Tribler system to two vulnerabilities. The one is that users are vulnerable to researchers sending them malicious Pickles. But that direction of researcher to client transmission is protected by signatures, so you can only accept Pickles from certain researchers. But the other direction is more interesting. So when researchers go crawling the network, it's possible for clients to send them any Pickles they want, and the researchers will accept them. So they also had a vulnerability that permitted the researcher or the researchers to be owned by their clients. Then the final example is in Red Hat Enterprise Linux 6. So this is a privilege escalation flaw in Enterprise Linux 6. And Enterprise Linux 6 has got a firewall configuration tool that's graphical called firewall or system firewall config. And system firewall config is normally only available to the root user in the default configuration. But in campus-style networks where you have many users, it is possible to delegate the ability to configure network firewall rules to individual users who are not root. And you do that using PolicyKit, which is a framework. In other words, you can say only these users, or you can assign to individual users the ability to configure their firewall without giving them full root access at all. And that is required because in order to create and share printers, you need to modify firewall rules. So anyone who's got the ability to share printers on a large-scale Red Hat Enterprise Linux deployment and isn't root is vulnerable to this issue. And the reason for this is because, again, it should be clear, there are two parts that communicate using Pickle, and one of those parts has got a very different trust level. The back end of the configuration runs as root, and it talks to the front end using dbus, which is a message passing service on Linux. So the front end talks as a regular user, the back end runs as root. And so let's do a quick demo for that. So what we've got here, I'm a regular user. What I want to show you is that I cannot sudo, so I'm not part of any particularly special group, right? That's not allowed. What I will mention is that this exploit that I'll show you is going to rely on the fact that SE Linux is disabled. If it is enabled, you can still hose the system, but you can't get a shell. So you can trash the system, but without a shell. You only get to certain files you're allowed to overwrite. So this is a pretty one-shot exploit again. Our shellcode is embedded inside of this Python file. What it does is connect to dbus. It'll pop up a password to verify that we are our user, and that's because we have access to this particular action via PolicyKit to configure the firewall. It'll write the pickle onto the dbus, and that pickle will spawn a listening shell. So it asks us for our own password. That's because PolicyKit is verifying we are who we say we are, but it's not asking us to enter a root password. And as I showed you, I don't have access to sudo or root permissions. This just allows me to access the firewall configuration tool only. So it runs. It looks like our shellcode was somewhat successful. We've got a listening shell on localhost, and you're now running as root. Okay, so to quickly wrap this up, what are the protections you can look for in terms of Pickle? So the basic idea is if you don't need Pickle, don't use it. If you're just trying to carry data in a structured way, rely on something else, rely on JSON. If you need to use Pickle, then make sure you have to ensure that both sides are as trusted or equally trusted and that they trust each other completely. Across the network, protect yourself either by signing your Pickles or implement transport layer protections. When you are writing to databases or to file systems, make sure that no one else can change that. Again, this is all about trust. I will put in one slide here about unsafe picklers. So you may have read of the idea of subclassing a pickle in order to whitelist or blacklist what gets loaded. So all I want to leave you with is it's really hard to do it properly because it's possible to escape an unsafe or a safe unpickler using 4 built-in methods. So there's some shellcode that'll get you out of a supposedly safe unpickler. So don't try and sanitize, either trust or reject. Some considerations, less important, and that is the summary. What we did today was I showed you the background to the Pickle virtual machine. I covered how it works. I covered a number of attack scenarios for breaking Pickle applications. I showed you how to write reliable shellcode using a high-level language that uses a tool that we released. We've released as well a tool for analyzing Pickles as well as that library. And then lastly, I showed you a number of real-world examples of this bug. Are there any questions? That looks great. Thank you.